So very good morning to everyone. Today I will discuss about our recent activity at Institute of Nanoscience and Technology towards designing supramolecular peptide polymer conjugates for precision nanostructure design and strain stiffening materials. So in our group, we are working on mimicking different biopolymers, and that's why we call it biomimetic material. We work on different polymer peptide materials and peptide polymer conjugates to show very interesting functional behavior. However, in this today's talk, I'm going to discuss about how we can have peptide nanofibers or nanosheets, and how we can impart precision in those structural design, and how we can extend it to functional interesting characteristics of strain stiffening material. Now, our inspiration towards mimicking such nature has been to look at the nature, understand how nature performs their engineering. And if you look at the honeycomb or very precise water crystals, they are very precise in nature. And in fact, if you look at also the the primordial soup from where nature start to design its own precursor of the building blocks, and eventually they can form a bottom-up self-assembly to form protocells. That is really intriguing. And if we have to really understand and perform self-assembly just like nature does, we need to understand systems which are non-equilibrium, and it can actually give interesting characteristics like exponential growth or self-replication. And but what happens is that in the lab, whatever the self-assembly we perform, they are actually thermodynamically driven, and they are dictated by the free energy change. However, nature it performs self-assembly in non-equilibrium way, which are kinetically controlled, or it can also have a dissipative energy control. And so the challenge is to dictate the shape and size of such bottom-up self-assembled nanomaterial, and how to impart very interesting adaptive and emergent behavior with functional control. So so our inspiration has been the A beta amyloid self-assembly, and such amyloid self-assembly happens in a non-equilibrium way, and it can form diverse nanostructures. And one of the characteristic of such self-assembly is that it actually shows exponential growth. Hence, thus, we designed short peptide amphifiles where in the N terminus we have got hydrophobic group, and the C terminus we have got hydrophilic group. It can, if you on a judicious solvent choice, if you dissolve it, it forms very nice nanofibers, and nanoparticles. These nanoparticles can get converted into kinetically controlled nanofibers, and which on repeated annealing can form very nice twisted bundle. Now, these nanoparticles are on pathway because they immediately get converted to nanofiber. So when we looked into the nanofibers, they are pretty much polydisperse in nature. We have looked into the polydispersity index of the length distribution of this fiber, that is 1.52, which signifies that definitely this is not a thermodynamically controlled self-assembly, which is otherwise PDI would have been more than 2. So then we thought that if we can make a very nice seed, uniform seed, now that would be excellent. So we did studying, and we formed seeds of lower PDI, which is close to 1. And now these seeds we employed with different ratio of nanoparticle, and to form different length distribution of resulting fibers, which we also have looked into the length distribution using histogram analysis. And we could see that we can make nanofibers of 1.2 micron or around 600 nanometer based on the ratio of monomer and seed. And such nanofiber can be such nanofibers or seeds are living in nature. You can keep on adding more and more monomer, and it actually keeps growing. And that is very important in nature, because if we can cross-link somehow this material, you can generate very uniform functional control of such hierarchical material. And now whatever we showed so far, that is rather on pathway control over the nanoparticle. However, many a times that is not really that elegant. So we wanted to really understand how we can really control the monomer stability, which will eventually retard the spontaneous growth of the self-assembly process. So then we thought is that can we really, that active monomer, can we really sequester into something off pathway state, so that as and when we require it, we can activate it and perform the controlled self-assembly. So in order to do so, we actually design a interesting interesting azobenzene unit onto the N terminus. And what happens is that this azobenzene can be irradiated with light to make cis analog. And with that, we thought that this can be used as photo cue. So basically you take a trans monomer which is active, and with an light and the active, and it can form supramolecular polymerization. However, if you go into cis, it actually goes into a dormant state, where crossing this activation energy barrier is rather difficult. But however, at a suitable activating visible light, it can actually come back and you can form this self-assembled supramolecular polymer. Similarly, we can also do the thing with the chemical sequestration, where you can take alpha or beta cyclodextrin, and it can actually trap this active monomer into the such chemodormant state. However, if you put an competitive guest like adamant and amine, it can actually come back to the active monomer, and it goes for the self assembly. Thus, what we have shown that we can take this trans 1 fiber, it can grow in supramolecular nanofiber, as you can see from AFM. You can use UV and visible light to get into dormant monomer, and you can actually get it reversibly. Similarly, you can show that we can actually trap that in dormant monomer state, and if you put adamant and amine, you can get very nice supramolecular nanofiber. Now, having done so, we also looked into the functional property of such peptide amphiphils. Because of this multiple amide bond, they are very nice, they have very nice spontaneous polarization, which can be utilized for looking at the piezo response. And we have seen, if you can have these chemo and photo controlled self assembly and disassembly, you can also control very nicely the piezoelectric response of this material, which is certainly a very interesting aspect. Now, we also have controlled the structural precision of the nanomaterial. So we took this preformed seed and put some put some of this chemo dormant state or photo dormant state, and using a chemo activation or photo activation, you can release such activated monomer, which actually goes, and that we follow it by CD, and you can follow the growth of the CD. And we have seen, upon the seeded growth, you can control very nicely the PTI of such material. And having done so, we also thought that can we really have it in 2 dimension. And for that, what we have done is that for such kind of amyloid peptide amphiphile, in the N terminus, we put now an interesting moiety called coumarin moiety. Now, coumarin moiety has a very interesting reversible photo cycloaddition adduct. They can form at 320 nanometer. They can form the cyclobutane adduct, which can be reversibly cleaved by this 254 nanometer light. And what it does is that if you take only this peptide amphiphile, of course, they will go for a on pathway metastable nanoparticle, which will eventually form nanofiber. However, if you can actually sequester using a gamma cyclodextrin moiety and followed by light irradiation, it forms not only fiber, in this case it forms fiber, but if you irradiate it, it actually forms very nice 2-dimensional nano sheet. So we thought that can we really control the shape and the size of such nano sheets? And as you can see, we have followed it. We can form very nice nanofiber, nanoparticle, and then nano sheets are like this, you can see. And using a suitable seed and monomer, we can have very nice control over the shape and size of such material, which is in a way very new. Now, what I wanted to just say that all these peptide fibers, they have we have checked their persistent length to find out the stiffness, because persistent length is a measure that whether it can be called a semi-flexible filament or it is a rigid rod, and that matches pretty well with the actin filament. And that's when we thought that if it is matching with the actin filament, so this is actually closer to mimicking some of these microtubule. And can we really have a nonlinear elasticity just like microtubule for our system as well? And this is very important, particularly if you make a material or extracellular matrix from the synthetic peptides, so you can actually tune the ECM, the extracellular matrix elasticity, and that has a role in the stem cells differentiation. So we thought that's a very interesting idea, because if you look at many of these biopolymers, they show this kind of stiffening response upon applied strain molecule. And this is what is actually very important, particularly in the case of cardiac muscles, which actually can pump the blood in an uninterrupted fashion, and that actually stems from the ATP mediated actin myosin cross-linking, and resulting contractile material. But then how can you make a synthetic material out of it? So what we followed a model where it showed that if you can actually cross-link such rigid rods of fibers using a suitable cross-linker, then if you can pull this entire network system, the rigid rod will actually give a strain stiffening response. So having done that, and this is what actually we get to see in a composite of actin which are cross-bridged with the myosin filament, and when this slides because of ATP mediation, it slides to, it can actually generate such kind of contractile material, and it shows strain stiffening behavior. So what we did is that we took our material which has a coumarin unit onto it, which is, as you know, it can also photodimerize to make photofixated sample. And we took also a very interesting functional polymer where you have polynipam. Now polynipam, as we know, because of its LCST, lower critical solution temperature, it can above that temperature it collapses, and because of this collapse it can give very interesting thermoresponsive property. And we also have a copolymer in that which has some aldehyde that can form very nice ship base with the with this lysine unit. So what we did is that we took this intra-fiber photofixation, and it can form this cross conjugated network. And if you heat the system up, then it can it can collapse the system, and it can probably give strain stiffening material. We have also compared that with this photofixated sample, and in the photofixated sample as well, it does the job. And when we looked into the microscopy, we did see that the single filament of the peptides, they can be bundled together to form this kind of bundled conjugate network. Now we looked into the heat stiffening behavior in the covalently cross-linked medium, and in the case of physical cross-linking, where in the polymer that did not really have any aldehyde functionality, and we did see that we can have a very nice heat stiffening because of the polymer chain collapse. It shows a very nice stiffening behavior. And in the case of covalent cross-linking, we did see that it can have a very nice permanent memory of stiffening response. And however, the covalent network formation is very important, because that only shows a very nice nonlinear response, whereas in the case of physical network, you don't see such nonlinear response. Next, we wanted to understand how the intrafiber photofixation can result into difference in the mechanism for strain stiffening. So for that, we actually performed a differential modulus based nonlinear rheology. You can see that any of these rheology, if you apply stress, you initially get a plateau, that is actually plateau modulus, and but after that it shoots up. It actually gives a nonlinear response, and you can quantify that by this exponent m, which is the stiffening index. And you can look at for the non-photofixated sample or photofixated sample, and also the reversibly photodefixated sample, this m value that differs, and that has to do with the mode of their stiffening response. That can be either by bending of the fiber or stretching of the fiber. The most importantly, we can show that our fibers and the conjugated network, they show similar response, just like the neurofilaments. However, our synthetic systems are even better, because these are all phototunable as compared to those other natural biopolymer. We also have looked into the load bearing and thixotropic property of our material, and they show excellent thixotropic behavior upon higher stress, and that is a very ideal situation for designing biomaterial. And we have looked at some of the preliminary cell response in this U2OS cell, and we did see that we have a very faster cell subsistence, and you can see the development of the the cell fingers in the presence of such nonlinear material as compared to the supramolecular hydrogels. So, to summarize, what we have learned is that we can very nicely have a structural control, structural precision of material that can be translated into functional implication as well. And we have a very nice, stiffening response based on the such a functionally or structure functionally precise peptides conjugated with the functional polymer. And this work wouldn't have been possible without active collaborations and active participations of my student and generous funding from ACRB. Thank you.